Thank you very much for waiting and joining today. So what I want to present you, this may be a solution of the cold fusion puzzle. I would like to, So I would like to present you some new experimental results that can solve the cold fusion puzzle. From the view of nuclear physics, there are two puzzle points. One is the extraordinary high penetration probability for tunneling effect, and the next is the different branching ratio from the experiments. Usually with higher edges, with the accelerator technique, we have two main reaction channels, neutron and proton channel, that are equally strong. And helium-4 channel is very weak. It's about 1 million times weaker than other channels. And at room temperature, we have opposite situation. Helium-4 channel is much stronger than both others. So we can start now with this tunneling effect, which is the main factor describing cross-section at very low energies. We are dealing with energies very deep under Coulomb barrier, and then we can use the penetration factor, which is very low. You can use also for element production in stars, and you see the dependence is very strong. Energy dependence or temperature dependence, this exponential function. At very low energies, however, it is important not only to describe reacting particles, but also the surrounding, the environment. Because if you have free electrons, once again. Okay. So if you have free electrons, they can be collected just between the reacting nuclei and can shield the Coulomb barrier. It can be made here using the so-called screening wave function. And if you develop this function into Taylor series, the first term we can take the first term, which is energy independent. This parameter is called screening energy. And if you want to include the screening energy effect, electron screening effect, it's very easy to do it just by increasing the energy of neutrons by screening energy. You should add the screening energy in the penetration, in the expression of the penetration factor. So this kind of measurements using accelerator technique has a very long story. We started the first experiments already in the 19th last century, and we have just neutron beam and used targets, metallic targets, with hybrid targets already implanted, neutron implanted targets. We measure particles, protons, tritons, and helium-3 particles by means of detectors, solid-state detectors, and we can measure angular distribution. You see the lines are very clear without any background. So even at very low energies where the cross-section is very low, you can make it very, very precisely. And the results, you see, this is a comparison of measured reaction yields compared to the theoretical predictions. If they will be the same, we should have the constant curve equal to unity of all energies. neutron energies. You see down to 5 keV we have measured. And what is also to observe that we have an enhancement of the measured experimental cross sections or yields down to lower energies. And this enhancement is because of the screening effect. So we can fit the curves using one parameter, screening energy, and the numbers you can see here. If we use different metallic environments, aluminium, we get a screening energy 190 electron volts, for zirconium about 300 electron volts, and for titanium 320. So it depends on the target, on metallic environment, and compared to gas targets, where the people got 25 electron volts, it is much larger. And you should keep in mind this exponential-like enhancement. So if we extrapolate the curve down to room temperature, we will have very strong enhancement at room temperature. Comparison to the theoretical values, you see we have applied very nice theory, the electric function theory that can include different components for electron screening effect coming from free electrons, coming from bound electrons, and from the lattice. All together give us the values which are significantly smaller than experimental one, with a factor 2 or 3. If we present our results in other scale using so-called electron gas parameter, this is just the distance between electrons in metals, you see that our material dependence can be very good described by theory, but it's still missing this factor 2 or 3. And we have already made extrapolation down to room temperature 10 years ago, or even more, using this electric function theory and a special neutron potential inside metallic lattice. And then you see that the cross-section or reaction rates at below 10 electron volts is almost constant. Of course, the absolute value depends very strongly on the screening energy applied, 300 electron volts or 150 electron volts, and at room temperature, room temperature is 25 millielectron volts, we have a difference already 10 orders of magnitude. So if we put all this value on this diagram on the right, you see here you have screening energy values and the reaction rates at room temperature. It's very easy to calculate it using our formula and compare with the room temperature experiments. So if we would like to have or explain the experiments of Fleischmann cones of heating cells, we need screening energies of 500, 600 electron volts. But we can explain already with screening effect measured the experiment of Jones. He observed very low neutron emission. And here for comparison, Kunin theoretical values that have calculated for neutron molecule using different screening values. So if you use our experimental screening values, we have enhancement about 40 orders of magnitude. So there were first experiments we made already many years before, and there were many problems. The experiments results have been confirmed by different groups, and there are different values coming from different groups. The problem was high vacuum we have used for the experiments because of target contamination. So what we can do is we can improve our vacuum in the vacuum chamber, and the next step is going towards ultra-high vacuum system. And here you see the system we have used. we have used at the Humboldt University in Berlin a few years ago. We have ECR, ion source, analyzing magnet, and diagnostic system. And what we get was 10 to minus 10 millibar compared to high vacuum 10 to minus 6, 10 to minus 7 millibar. So here you see our results. And the problem is, once again, even at ultra high vacuum systems, that we have still contamination coming from oxygen and carbon. Here's Auger electron spectroscopy, which is very sensitive. You can measure even contamination of less than one monoatomic layer. So the problem was at very low energies, you need to measure much longer, many hours, many days. And then you see here is our screening curve, one parametric fit, but at lower energies, below 10 kV, we have some deviation, and the reason for that is just particle contamination, even at ultra-high vacuum. And here you see, but this also what we have expected. High vacuum value for screening in zirconium was 300 electronvolts, theoretical value 97 electronvolts, but if you improve vacuum, we get about 500 electronvolts, much higher. So it was something what was very, very nice for us. Okay, sorry. Okay. But this is not all of the thing, because as I mentioned before, we need something additional. We should change also the branching threshold if we want to explain cold fusion. So already many years before, we proposed that there should be a resonance very close to reaction threshold. Here's the reaction threshold value 4. This excitation energy of about 24 MeV. The levels, the resonance levels of helium-4 are very well known, and they have structure just 3 nucleon plus 1 nucleon. Only this resonance, highly excited resonances at energy, excitation energy of about 30 MeV, and they have different structure. They have deuteron plus deuteron structure. And the origin of this structure is not known till now. So what we have proposed, there should be a threshold resonance very close to the reaction threshold, and the structure of this resonance should have a nuclear molecule structure, just presented here. If you assume this kind of structure, we can have a proper sequence of the levels, just as deuteron levels. And what is missing, however, if you put the wave function and calculate the sequence of the states using this correlation diagram, this just missing this 0+ state, which should be also observed. But the problem is, if you have resonance very deep under Coulomb barrier, the width of this resonance will be very, very small, electronvolts instead of usual case in nuclear physics, mega electronvolts. So it is very difficult to find out this resonance experimentally, and therefore I would say nobody have seen this resonance till now. This resonance should be also observed in our experiments. If you look at our cross-section, total cross-section, once again we have here this enhancement curve, just a ratio between experimental and theoretical values. You will see once again in zirconium this classical enhancement curve. But to our surprise, we have two different points once again here. One is that if you use only one parameter, screen energy, you have the energy, screen energy 110 electron volts, which is very close to the theoretical one. And you have expected, of course, very high screen energy. Here you have very low screen energy. And the shape of this curve is, cannot be described using screening. You know, screening curve is in blue, and you see systematic deviations from that one, and only if you use resonance contribution, use our interference effect of this resonance contribution to the one of 16 matrix elements we have used, this T-matrix theory we have used, which are already known for DD system, we can describe this curve correctly. This not only this, we can use our resonance hypothesis to describe branching ratio, neutron-to-potential ratio for strontium experiments, where we have observed for the first time a neutron channel suppression. We use neutron with 10 millielectron, proton with 40 millielectron, also anisotropy angular distribution for neutron and proton channel. So finally, this is also something that was also very important. If we measure the enhancement factor during the time, we have used already several hours in the beginning of when the target was very clean. But if you wait a little bit longer, we measure enhancement factor much higher. So this point corresponds to this 100 electron volt screen energy. But if you wait 4 or 5 hours, that we have screen energy 500 electron volts. So it depends on the time. But what is the time? The time is the number of crystal defects. There is only 1 or 2 atomic monolayers. There is no absorption or contamination that can disturb the screening effect. So it is only crystal lattice defects. That means it is something what we can reproduce by effective electron mass. And we can have these values of screening for all the cases. So we can control, even control screening energy and control reaction rates at room temperature, because if you know what is the structure of material. So if, in conclusion, we have very strong screening effect, but the screening energy depends on the surrounding, on the structure of the material. This first conclusion. The second conclusion, we have indication for 0+ resonance in helium-4 that increase reaction rates at room temperature by 6 or 7 orders of magnitude. So we can explain heat production and even non-reproducibility in some experiments. And finally, you see here our new setup at the university in Szczecin. This ultra-high vacuum facility. We want to go towards lower energies because the energy function of two different components, screening component and resonance component, are different. And if we continue our experiment towards lower energies, we can distinguish much better between different components. So we will have, or already have, milliamps on the targets, and ultra-high vacuum with a very nice diagnostic system, electro-ultra spectroscopy, XPS, UPS, scanning points, argon gun, and so on, and very, very nice vacuum value, 10 to minus 11 millibar. So our aim is to go towards 1 kb or even below. This in center mass of system 500 electron volts, and you see the cross section drops very quickly towards lower energies, but the enhancement factor should reach the values of about 100,000 at this energies. So we can distinguish much better both components. And finally, the people. that contributed and were involved in different experiments. And finally, this very nice picture we use to present another project, because we thought if we would need some money for cold fusion experiments, this may be a very good also to study fission reactors. So this is a new kind of fission reactor, which gives a very nice electricity to 1/10 prices, cheap hydrogen, and so on. You can visit our internet site. Thank you.
A question and a comment.
Well, thank you for a very nice presentation. It's a pleasure to see such equipment and real science done. My only concern with the electron screening is that it might be good to explain